Hello everyone, let's solve the problem single element in a sorted array. You are given a sorted array consisting of only integers where every element appears exactly twice, except for one element which appears exactly once. Return the single element that appears only once. Your solution must run in O of log n time and constant space. Alright, I have three solutions for this problem. We will see one by one. Okay, and if you want to look at the most optimal solution, that is the log n time solution, I will attach the timestamp. You can directly skip to it and watch from there. Alright, let's see what the problem is saying. We are being given a sorted array, right? And every element in this sorted array would be in pairs, right? That is two times, but one of them would be only one time. So we are supposed to return that number, right? In this array we can see 2 appears only one time, right? But all the others appear twice in pairs, so we are supposed to return this. So what will be the naive solution of this approach? We will go through the whole array, and on the go we will find out the element which appears only one time. How? Let's see. Let us say we start here. Now we know it is supposed to be in a pair, right? We will check the previous element. Is it equal? Yes, that means it's in a pair. Let's move up here. We will see, is the previous element the same? No. That means this is our odd one out. We will return this. Say we have something like 1, 1, 2, 2, 3, 3 and 4. We'll start here. Previous element is same. Fine. It's in a pair. We move here. Previous element is same. Fine. We move here. We see previous element is same. Fine. We move two places. We are out of bounds. On the go, if we are not able to find the odd one out, we will simply return the last element, right? Simple. So what we are doing, we are moving by two places and we are assuming that the previous element is also same as the element on which we are currently standing, right? If it is not, then it's not a pair. Why exactly? Because if this is a element and its previous is the same, we form a pair. Now we go here. This one is also is supposed to form a pair, right? We move two places, right? We can't, if the element here is not same as this one, right? There is no way this is going to form a pair, right? Because when we were here this already formed a pair, isn't it? Right? Let us see the code. So this is the code. We'll start from the first index, and we will go till the end, and we will jump two places at a time. If the previous element is not the same as the current element, that means the previous element is not in a pair. We will return it. Otherwise, the last element is the odd one out, isn't it? Say we have an array. This can be edge case, right? We have this. So that means we will not loop at all on this one, right? We don't have a index 1 in this one. So in that case, what will happen? We have this one, right? We will return index nums dot length minus 1. That is, nums dot length is 1, minus 1 is 0, nums of 0 is this one only. This is the single number. We'll return this. Fine. Let's see another approach. In this one, we are going to use the idea of bitwise operators. Which bitwise operator? XOR operator. Now what does XOR do? We know if we do a XOR of 0 with a number say a, we get a. If we do the XOR of two same numbers, we get a 0, right? We are going to use this idea. Okay, what will happen? Say we have this array a b c c d d. We will take a variable, say answer equals to 0, and we will run a for loop and take the XOR of all these elements. Okay, now what will happen? These pairs, when we do a XOR, they will turn to a 0, right? 0 0, and in the answer we will be left with this one. Pretty simple. Let's try it. A XOR a, then we go to b, then we go to c, then we go to the another c, d d, right? This and this, this and this, this and this are going to give us 0, right? And 0 XOR b is what? 0 b only, right? Saw that. So this is the code for this approach. We initially take a variable answer equals to 0, and we iterate, and we do answer equals to answer XOR I at each step. Then we return answer. It will contain the single element. Fine. So this approach as well as the previous approach both have a runtime of big O of n and a space complexity of big O of 1, that is constant, right? Now let's talk about our final approach. We have been given our solution must run in O of log n time and space should be constant. And we know our array is sorted. What does that mean? We have to use binary search, right? Okay. Now this is not going to be a straightforward regular binary search, right? Because we have not been given any target. So let's see how are we going to apply binary search in this one. So initially we will have our left and low and high, right? Low and high pointers. We will as usual calculate the mid. What is mid? This is the mid. Now we are stuck. We don't have a target, right? We don't know which side to go. Should we go this side or should we go this side? Now let's see one thing. We know our elements are in pairs, right? So let's take this one. 2, 2, 3, 3, 4, 4. So all the numbers in this are in pairs and the size of this sequence is even in nature, right? Similarly, let's say 2, 3, 3, 4, 4, 5, 5. All are in pairs, but we have a single number here. In this case, our size of the array will be odd. We will use this idea to reduce our search space. We will use this idea to decide which side to move. All right. We are at mid. Okay. We will check both sides of mid. That if there is an equal element. That is, if we have a 3. Okay. If we have a 3, means 3 is in a pair. All right. If both the elements on both sides are different, that means 3 doesn't exist in a pair. We will right away return the middle element. Okay. Otherwise, we do our work. What will we do? We will take this subarray. Okay. We can take this one also or this one. We can take any one of them. I will go with this one. We will take this subarray and we will see if the size is even or odd. We can see that it is even. Okay. It's even. Now we will see that this is our middle element. Now for our middle element, where does the other element same as our middle element lie? That means, I mean that if we have a 3, in mid we have a 3, where does the other 3 lie? Does it lie to the left or lie to the right? That means it lies to the left means nums of mid is equals to nums of mid minus 1. If it lies to the right means nums of mid is equals to nums of mid plus 1. Okay. Now we can see that the equal element lies to the left. Now what does that mean? This means that our pair is here and all these elements inside this subarray are also in pair, isn't it? See, all are in pair, it's even in size. Okay. Now what if our element would lie in this side? Let's say we have a 3 here. This would be our subarray. The size would be odd. Okay. We see that our element lies at the right. That means we haven't included this one, right? That means if we exclude our equal element, that is 3, the rest of the elements inside this subarray are in pairs. Listen very carefully. If this 3 lies in this subarray and our middle element is out of this subarray, right? That means if we exclude this one, then rest of the elements inside this subarray are forming pairs. Clearly they are forming pairs, isn't it? Now we know that in this side we don't have a single number, that because each of them are in pairs, right? So our task is to discard all of them. We won't check this side. We will go to left side, right? We will go to left side. Okay. Now we will move our high pointer. Where will we put it? This is our mid, right? Generally we do mid minus 1, but this one is again the same element. We won't consider it, right? We will put high here. All right. We will put high here. Now this is our search space. So this is our search space now. Okay. We will calculate mid. This is no more the mid, right? This is no more the mid. This is our mid now. Okay. Now we will, leaving the mid, we will get the size of this subarray. What is it? It's the size is 1, which is odd. Fine. And the middle element, it's 1. Where does the equal element, where does its copy lie? It lies to the left side, right? It lies to the left side. Now what does that mean? It means that if the equal element of mid lies to the left side, and the size at the right, the size of the right subarray is odd, that means our duplicate lies this side. So this is another case. Okay, say we have this see, say this is mid, this is left, this is say high. Okay, we take this size and we find out that it is odd, and we see that the element which is at the left is equal to our mid, right? What did we see in our previous case? That if our mid element is equals to the left of mid, that means and the right subarray is even in size, right? That means they are in pairs. But if it is odd in size, okay, that means there is a single number in that right subarray. So in that case, we will move our left to the next of mid. Fine. Okay, so we move left to the next of mid. Finally we are here at the single number. So this is what we return. Okay, let's try to build our algorithm from this. First we did what? We computed mid, right? Mid. Then we did what? Then we saw if right subarray after mid is even or odd in size, right? Now if our mid is equals to mid minus 1, okay, and what if our mid is equals to mid plus 1? Okay, if the mid is equals to the previous element, okay, and the right subarray is even in size, that means we won't go to that size, right? All the elements in the right subarray are in pairs, so we won't go to that side. What we will do? We will go to our left subarray. That means we will decrease high. We will bring high to the left. That means we will bring high to mid minus 2. Why mid minus 2? Because this is 3, this is 3. The right subarray was even in size, right? This is a duplicate element, right? We don't want to check it once more. We will skip this one and we will put high here. That is mid minus 2. Fine. If it is odd, that means our single number lies to that side, our right side. In that case, we will increase our low to mid plus 1. Why mid plus 1? See, mid and mid minus 1 are same, right? Minus 1, and we have a duplicate element this side, right? So we will put our low here, isn't it? Because our work till this side is done. So we'll put mid low at mid plus 1. Otherwise, if mid is equals to mid plus 1, say this is mid, and mid plus 1 are equal, and if the subarray at the right is even in size, okay, what is even in size? What does that mean? 4 4 5 6 6. This is the only way how the right subarray can be even in size. Let's see. 3's duplicate lies in this one, this subarray. 4 and 4 lie here, 6 and 6 lie here, and there is a single 5. That extra single element would make the right subarray even in size, isn't it? If it was not there, then it would be odd in size, isn't it? In that case, our single number lies this side. We will move our low to here. Low where? Put where? Low equals to mid plus 2, because we want to skip this duplicate element, right? Otherwise, if it is odd in size, we just saw now, If it is odd in size, how can it be odd? 3, 4, 4, 6, 6. These two are in pairs, right? And we have this extra duplicate of our mid that will make our subarray odd. That means we won't check this side. We will go this side. Our high would become mid minus 1. Why mid minus 1? Because the duplicate is at right side. That means our work till here is done. The elements we should check would be right from the previous element of mid. We did mid minus 2 only when our duplicate was at left, isn't it? I hope that it's clear. So this is basically our algorithm. Okay, now we will try to code it, then we will discuss some more things. Int low is 0, high is nums dot length minus 1, right? Okay, while low is less than high. Why less than high and not less than equals to high? We will see. Okay, int mid equals to low plus high minus low by 2, not low plus high by 2, because we don't want to cause an overflow, integer overflow. Okay, now if our current mid is not equals to nums of mid minus 1, that is the element at its left, and it's also not equals to the number at the right, that is mid plus 1, both the elements at both the sides are not equal, that means it's a single number, so we will return it nums of mid. Okay, but if it was not a single number, we will calculate the size of the right subarray next to mid. Okay, how will we do that? Let's say boolean is say even, is the right side even? Okay, that will be high minus mid modulus 2 equals to 0. Say this is our mid and this is our high. Okay, high minus mid will give us the size of this subarray, isn't it? Okay, if is it equals to 0, that means is it even? That thing will be stored by our boolean is right even. Okay, now what was our task? To see is mid element is equals to the mid minus 1 element. Okay, is if nums of mid equals to nums of mid minus 1, is it equal? If it's equal, we will do something. Otherwise, if nums of mid is equals to nums of mid plus 1, then we will do something. What will we do? If this is the case, we will see is the size even. If is right even, if it's even, do something, otherwise do something else. Similarly for this one, check if it's even, is right even. If it is even, do something, otherwise do something else. Now if it is even, move high to mid minus 2, right? We saw that. Why mid minus 2? Because if the right side is even and duplicate lies this side, that means all the elements in this side are in pairs, so we will skip this one as well as the duplicate and we will place our high pointer here. Fine. Okay, if it is not, that means if it is odd, and duplicate lies to the left, that means they are not in pairs, there lies some imposter, there lies a single element. See, when it's a single element, it would make the size odd, isn't it? So we will move our low pointer to here, next of mid. Low equals to mid plus 1. Okay, done. Now what if this is the case? Is it even? Yes, if it is even, move low to mid plus 2. Low equals to mid plus 2. Why mid plus 2? Let's see. See, this is our mid and duplicate lies to the right, and along with the duplicate the whole subarray is making a size of even size, right? So if we exclude the duplicate, the rest of the subarray is making an odd size, right? That means there is a single number. We can clearly see that, right? Otherwise, if there was not a single number, it would have made a odd size, right? So in that case, we will move low to mid plus 2 by skipping the duplicate. Otherwise, we will move high to mid minus 1. Why mid minus 1? Say this is our mid. Sorry, this is our mid. Okay, and this size is odd. You can clearly see that we don't have a duplicate here. This one is the I mean, there is no single number. This one is the duplicate, and the rest is making a pair, right? That means our single number doesn't lie this side. We'll move to this side right before this mid, isn't it? So mid minus 1. At the end, return nums of low. Now why nums of low? Let's see. We had taken this low less than high, not equals to, right? Less than equals to, and this nums of low. Let's try to understand why. We have 1 1 2 3 3. Okay, 1 1 2 3 3 4 4 8 8. In normal binary search, what do? We do less than equals to, right? But here we are doing only less than. We want both the low and high pointers to come and stop at the same position. They are doing nothing but coming to the single number from both sides. Okay, if we do equals to high, okay, at the end they both will stand at the same position. If we do equals, if we do a equals, we are still giving it scope to, cross each other, right? They will move up. Why? Because if it is say equals to high, we will again calculate low, mid, then we will check this condition, then we will do all these things, right? And our eventually our low and high would move up, isn't it? But we want both of them to come and stop at the same place, right? In this example, what we are doing, how everything is happening. At first, this is our mid, this is our mid, our high moves by 2 positions, right? And this is our low, it moves by 2 positions and comes here, and we want it to stop right here. Okay, and if we do a equals, they will try to move away from here, and we won't have a record of our single number, isn't it? So this is why we have put this condition, and we are returning nums of low. If we return nums of high, that's the same thing, because they are both at the same position. So this is why we are returning nums of low. Now let's try to run it. We remove this. What is the issue? Nums of low. Okay, nums of mid. Oh shit, it's mid minus 1. There we go. So this is our solution. The time complexity is of course the O of log n, right? So this is pretty much about this video. I know this is a bit complicated. It's not a regular binary search, and it's a modified binary search, right? So if you like this video, hit the like button, share this video to your friends, and definitely subscribe, and I will see you in the next video. Bye bye.